In this video, we're going to cover section 8.3, polar form of complex numbers, de Moivre's theorem, part 2. So this is the section where we're going to focus on de Moivre's theorem. We have two examples that we want to do, but before we do that, I want to explain something real quick. And that is that de Moivre's theorem has to do with taking powers of complex numbers. Our first example will be to raise the complex number to a positive integer. And the second example will be to find a root of, or a square root or a cube root, or in the case of our second example, the fourth root of a particular complex number. Now, in general, that might be difficult, but using de Moivre's theorem, if we can turn our complex number into its polar form, then de Moivre's theorem gives us a very nice and simple way to calculate the complex number raised to a power, or the root of a complex number. And so that's what we're going to do in these two examples. So our first one says to find 2 plus 2 squared to 3i raised to the 5th power using de Moivre's theorem. I would like to point out that by example 2 of part 1 here, so part 1 of the section 8.3 video, we have that 2 plus 2 square roots of 3i is equal to 4 times cosine of pi over 3 plus I sine of pi over 3. And so that is our polar form of 2 plus 2 squared to 3i. To calculate that value raised to the 5th power, we want to use de Moivre's theorem, so it's just looking up what that is right now, and we're going to use that then to find the 5th power. So I want to take 2 plus 2 squared to 3i. We want to raise this to the 5th power. This is 4 times cosine of pi over 3 plus I sine of pi over 3 raised to the 5th power. Well, to do that, we take 4 to the 5th, and then de Moivre's theorem says that this is 4 to the 5th, and then times cosine of that 5, that power, times the angle, plus I sine of 5 times pi over 3. And really, this is just repeated use of the product rule that we used in that previous video, right? We did z1 times z2 in example 3 of the previous video. This is really just comes from repeated use of that. All right? So here we got 4 to the 5th times cosine of 5 times pi over 3 plus I sine of 5 times pi over 3. Well, what is 4 to the 5th power? That is 4,096. And then we have cosine of 5 pi over 3 plus I sine of 5 pi over 3. And that's it if we want to leave it in polar form. We could recalculate this and write this back out into our standard complex number form. So to do that, what is cosine of 5 pi over 3? Well, that is 1/2. What is sine of 5 pi over 3? That is negative square root of 3 over 2. So this is 4,096 times 1/2 is 2,048 minus 2,048 square root of 3i. So if we wanted to write it in our complex number form, the normal, or the standard way to write out complex numbers, it is 2048 minus 2048 squares of 3i. All right, like I said, we had one more example that we wanted to do, and that is to find the fourth roots of negative 256i. To do that, we need to know its polar form. So I want to think about drawing out the real or the complex plane. So we have the real axis here, we have the imaginary axis here, and then negative 256i is somewhere way down here on the imaginary line. Now we have negative 256i is equal to, now what is this? Well, if we think about what cosine is, cosine should be 0 here because we went straight down. And sine should be negative 1. Well, what angle do we use to go straight down? Well, that is 3 pi over 2. So we have cosine of 3 pi over 2 plus I sine of 3 pi over 2. And then we have to multiply by our modulus out here. Well, this is 0 and this is negative 1. So what is the modulus to get negative 256i? Well, that's 256. Right? Modulus is just the length of the line from the origin out to our point. So what is the length of that line? Well, that is 256. Okay, so this is our polar form of negative 256i. And the nth roots, so if we used a Walrus theorem, the nth roots of z are, and this is w sub k is equal to r raised to the 1 over n times cosine of theta plus 2k pi all over n plus I sine of theta plus 2k pi all over n. All right. And then this is true for k is equal to 0, 1, all the way up to n minus 1. And this gives us our nth roots of z, right? And there are n of these here from k equals 0 to n minus 1. That will produce n of these answers. So if that's our form for each one, well, I just want to plug that in. Then this tells us that each value is w sub k is equal to 256 to the 1/4 power, right? We're going back to our question here of what is the fourth root of negative 256i. So that is 256 raised to the 1/4 power times cosine of, well, the original angle was 3 pi over 2 plus 2k pi all over n, which is 4, plus I sine of that same thing, 3 pi over 2 plus 2k pi all over 4. So w sub k is equal to 256 to the 1/4 power is 4. And this is cosine of 3 pi over 8 plus 2k pi over 4 is k pi over 2, or in other words, pi over 2k, plus I sine of 3 pi over 8 plus pi over 2k. And that's it. This will give us all 4 results. If we plug in k equals 0, we get 4 times cosine of 3 pi over 8 plus I sine of 3 pi over 8. That'll be 1/4 root of z. If we plug in k equals 1, we'll get the second 4th root of z. Plug k equals 2, we'll get the third 4th root of z. And if we plug in k equals 3, we'll get the 4th root of z. And so again, just plugging those 0, 1, 2, and 3 in, we'll get all 4 fourth roots of z. And that's it for this section.